Okay, today we're going to look at some examples of translating between tables and expressions. And you remember that an expression is a combination of letters that represent a number, so variables, and an operation. So an algebraic expression has to have at least a variable and an operation, and there might be some numbers or constants in there as well. So we're going to look at taking the information that is in a table and making it into an expression. And here's a little tip up here. This is something from one of my units. Tip for students that to find an expression, they can try adding, subtracting, multiplying, or dividing. And if that doesn't work, try a combination of operations like multiplying and adding or multiplying and subtracting. So we'll look at some of these. Some of these are fairly obvious to us. They might not be as obvious to students if they don't remember some of these relationships between weeks and days, hours and minutes, etc. Um, so we start with something a little bit more simple like this, so students can kind of rely on that idea, that knowledge of relationships, and see how it works in a table. So in a table like the first three, we have two columns, left and right. And so as we're looking at the relationship, we're looking from left to right. And what do we do to one number to get to the other? What do we do to 1 to get to 7? What do we do to 3 to get to 21? What do we do to 4 to get to 28? Now, sometimes students will try to go down here and they'll say, okay, I added 2 to get from 1 to 3, and then I added 1. Or they'll say, I added 14 to get from 7 to 21, but then I added 7 to get from 21 to 28. So they might get a little confused if they try to go down. But we're looking at the relationship left to right. So what do we do to 1 to get to 7? Well, we could add 6. We could multiply by 7. And I would start with something simple like that. First, does just adding or multiplying work? 1 plus 6 is 7, but then we have to test it out with the others. Is 3 plus 6 21? No, it's not. So that does not work. 1 times 7 is 7. Is 3 times 7 21? Yeah, it is. Is 4 times 7 28? It is. So I do tend to write this in here so students are seeing that we are taking what is on the left, multiplying it, and getting what is on the right. And so x times 7, so any number this is, it can be any number in the whole world, will get multiplied by 7 for this relationship. So 7x, or you could do 7 times x with the dot. Hours to minutes. Most of the time, students will remember that there are 60 minutes in an hour, so they probably will pretty quickly see that 2 times 60 is 120, 3 times 60 is 180. But if they don't remember that, they will have to think about what would I have to do here? If I had 120 divided by 2, what did I multiply by? And they could find it that way. They might try adding and say plus 118. 2 plus 118 is 120. But 3 plus 118 is not 180, so that doesn't stick. So times 60 for each of these. I'm not going to write it every single time here, but I would write it every single time for students so that they're understanding that we're doing the same thing every time from left to right. So our expression would be 60 times x, or 60x. Cars to wheels. Most of the time, students know that there are 4 wheels on a car. So if we take the number of cars we have and multiply by 4, we will get the number of wheels. But just in case they don't, we can suggest you can multiply by 4. You could add 3. If we multiply by 4 each time, we do get the number of wheels. 5 times 4 is 20. 6 times 4 is 24. So x times 4, or 4x, would be the expression we need. Now, these tend to get a little trickier when we first are going left to right because we've got columns, and then we switch to top to bottom because we have rows. We have the first position in, say, a sequence, it is 4. So the first position, the value of that is 4. So I've got a sequence like 4, 5, 6, 7, and the position of it, here's the first one, second one, third one, fourth one, fifth one, and so on. There are times when students look at something like this, and instead of going top to bottom, they will go left to right, and they will say 1, 2, 3, 4, 5. That means this is 6. 4, 5, 6, 7, 8. That means this is 9. And they'll simply write 9 instead of an expression, an algebraic expression using the variable. Or they might say, ooh, I added on 1 every time. 4 plus 1 is 5, plus 1 is 6, plus 1 is 7, plus 1 is 8. This must be x plus 1. If they were to go ahead and try that, if they did say it was x plus 1, and we always, encourage them to test it out to see if it works. If this was a 6, and we said that the expression is x plus 1, that would give us 7 here. And that doesn't work. So we always want to check our thoughts to see if it actually makes sense in what we've got going on. When we then go from top to bottom, as we should in this case, we could say, all right, we've got 1, I could do plus 3. Does that work? 2 plus 3 is 5, 3 plus 3 is 6, 4 plus 3 is 7, 5 plus 3 is 8. Cool. That works. X plus 3 is our expression. And my dog is snoring in the background, so if you hear it, I apologize. All right, position and value here. So now 1 to 2. Now this seems really simple. 1 plus 1 is 2. 1 plus 1. 3 plus 1, not 8. Okay, so that does not work. 1 times 2 is 2. That's easy too. 3 times 2 is not 8. That doesn't work either. So students might want to start with one of the larger numbers and see if they can figure out what happens. And so here I would recommend that they start with a list of what they're doing. Okay, so we could start with times 2 for the 3. 3 times 2 plus 2 gives us 8. 3 times 2 plus 2. 5 times 2 is 10, plus 2 is 12. That does not work. So we'll go in a predictable order and try the next one. 3 times 3, that is 9. So to get to 8, I would have to subtract 1. 5 times 3 is 15, minus 1 is 14. 7 times 3 is 21, minus 1 is 20. 8 times 3 is 24, minus 1 is 23. And we go back and check it with the 1. 1 times 3 is 3, minus 1 is 2. So that one works. 3x minus 1. All right, 2 to 7. We could do plus 5. 2 plus 5 is 7. 3 plus 5 is not 9. Okay, so I could do 2 times 2. So I could do times 2. 2 times 2 is 4, plus 3 is 7, right? 2 times 2 is 4, plus 3 is 7. Okay, 3 times 2 is 6, plus 3 is 9. 6 times 2 is 12, plus 3 is 15. 7 times 2 is 14, plus 3 is 17. 10 times 2 is 20, plus 3 is 23. So we would have 2x plus 3. And again, if we help students to just kind of go in an orderly fashion, not jump around and guess at it and say, well, maybe it's times 4, maybe it's times 5, maybe it's times 1, maybe I subtract after I multiply. If we go step by step here and we kind of make a chart, if you will, to kind of organize our thoughts, and we go up one at a time, times 2, then times 3, then times 4, and then test them out. That might help them get there a little bit more quickly than if they just kind of look at it and go, I'm not sure. If we go over here to the you try it, we've got 12, and we're going down to 1. So if students know anything about dozens, then they might very quickly say, okay, it's 12 divided by 12 because there's 12 eggs in a dozen. 24 divided by 12 is 2. 48 divided by 12 is 4. X divided by 12 is our expression. If they don't know that there are 12 eggs in a dozen, then they might try 12 minus 11. Gets us to 1. That doesn't work. 24 minus 11. So since we are getting smaller, their typical testing should be divide or subtract. And then they can, again, keep testing from there if they can't get it. But they should get that one relatively quickly. Okay, we've got a position and value again. This time the chart is going left to right. The table's going left to right. So we can go this way. We can start, since we're getting a small number to large number, we could start with add 6. 1 plus 6 is 7. 3 plus 6 is not 17, so that doesn't work. All right, so we could start with any one of these numbers and say, all right, I'm going to start with the 3 and 17, just because when I worked with the 1 to 2, that was a little tougher. I'm going to start with the 3 to 17, and I'm going to go in an orderly fashion here. 3 times 2 is 6. I would have to add on 11 to get to 17. Does that work with 4? 4 times 2 is 8, plus 11 is not 22. So that one doesn't work. Then I'm going to go with 3. Multiply by 3. 3 times 3 is 9. I would have to add on 8. 4 times 3 is 12. If I add on 8, I get 20. That does not work. I can multiply by 4. 3 times 4 is 12, plus 5, sorry about the sloppy, is 17. 4 times 4 is 16, plus 5 is 21. Close, but not there. Okay, then I can do times 5. 3 times 5 is 15, plus 2 is 17. 4 times 5 is 20, plus 2 is 22. 7 times 5 is 35, plus 2 is 37, and back to the 1. 1 times 5 is 5, plus 2 is 7. So we have the expression 5x plus 2. So I think setting students up with this kind of an orderly guess and check helps them quite a bit rather than just doing random guess and check. So that is about it for today. Those are our examples. If you have any questions, let me know.